Now today we will discuss about acceleration analysis by relative acceleration method, right? So let us discuss first basic things. Acceleration of a rigid link. Acceleration of a rigid link. We know that already the velocity, which means the rate of change of displacement with respect to time, whereas for acceleration the rate of change of velocity with respect to time, right? So we know that velocity is a vector quantity, it has both magnitude and direction, whereas like velocity the acceleration is also a vector quantity because it has both magnitude and direction. So now consider this figure, consider the link AB rotating about a fixed point A in the clockwise direction as shown in the figure. Now let omega be the angular velocity and alpha be the angular acceleration of point B with respect to a point A, right? We know that the velocity of point B with respect to A, the velocity of point B with respect to A is always perpendicular to the line joining of these 2 points AB, or the velocity of B with respect to A is perpendicular to the corresponding link AB. This is already we discussed, right? So now the components of acceleration. Now components of acceleration. The velocity of the particle changes in both magnitude and direction. Already we know that the acceleration, which means the rate of change of velocity with respect to time. Here the velocity of the particle changes in both magnitude and direction. Therefore, the component of acceleration is two. One is the radial or centripetal component or tangential component, right? So now radial component, how to calculate the radial component? The radial component, what is meant by radial component? The radial or centripetal component of acceleration acts in the direction parallel to the link, and its direction is towards the center. Centrifugal and centripetal, what is the difference? Centrifugal, which means the direction which is outward from the center of rotation, whereas for centripetal it acts towards the rotation, right? Again I will repeat, the radial or centripetal component of acceleration acts in the direction parallel to the corresponding link, and the direction is towards the center of the rotation. Here the velocity of B with respect to A, or acceleration of B with respect to A, right? Then how to calculate the magnitude for this radial or centripetal component? So this is the formula for calculating magnitude. The acceleration of radial component of BA, here the radial or centripetal component, tangential component. So it's simply called as a radial component and tangential component, right? So how to calculate the magnitude of radial component? This is the formula. Acceleration of radial component of BA, which is equal to omega squared into AB. Omega squared is nothing but angular velocity, right? So angular velocity squared into the corresponding length of the link, right? Now the direction of radial component is towards the center of the rotation, already we discussed, right? Then now tangential component. Tangential component is nothing but it's similar to the velocity diagram, right? The tangential component of acceleration acts in the direction perpendicular to the corresponding link. Already we discussed, right? Then how to calculate the magnitude for the acceleration of tangential component of BA? See, this is the formula. The calculation of magnitude for this tangential component. See, the acceleration of tangential component of this BA, which is equal to the alpha into AB, the length of the link AB. Alpha is nothing but angular acceleration. Alpha, which means angular acceleration of the corresponding link. Okay. Now see here, this is the acceleration of the total, the acceleration of the corresponding link BA, which means the addition of acceleration of radial component of the corresponding link and the acceleration of tangential component of the corresponding link. See here, the total acceleration of the corresponding link, which means the acceleration of BA, which is equal to the acceleration of radial component of BA plus acceleration of radial component of, tangential component of BA. Okay. So before entering into the acceleration diagram, we should follow the steps. So now let us discuss a simple problem, how to draw the velocity and acceleration diagram, right? So it's simple problem. So now I will read the problem. ABCD is a 4-bar chain with a link AD is fixed the length of the links are AB is 62.5 mm and BC is 175 mm, CD is 112.5 mm and AD is 200 mm. The crank AB rotates at 10 radian per second clockwise. Draw the velocity and acceleration diagram when the angle BAD is 60 degree and B and C lie on the same side of AD. Find the angular velocity and angular acceleration of the links BC and CD. So, what they are asking, find the angular velocity and angular acceleration. Angular velocity omega BC and omega CD, this is the angular velocity of BC and CD, whereas alpha BC and alpha CD. So, we have to find omega BC, omega CD, alpha BC, alpha CD, right. So, now already we discussed how to calculate omega BC and omega CD. So, anyway in this video we will discuss this also, right. So, our ultimate aim is to find alpha BC and alpha CD, right. So, this is we will get from acceleration diagram. So, let us move step by step. Okay. Now, step 1, construction of the configuration diagram. Already we discussed according to the given dimensions. First, we have to draw the configuration diagram, right. So, AD is fixed. So, the given in the problem, AD is fixed. So, this is AD and AD which is equal to how much? 200 mm. So, draw a horizontal line with 200 mm length, that is A comma D, right. So, this is a fixed link. Now, we have to draw a inclined line with 60 degree, right. So, and AB which is equal to 62.5 mm, take a compass and measure 62.5 mm and take A as a center point and cut the arc, right. So, then we got B. Now, we have to find C, right. So, BC which is equal to 175 mm, right. So, take a compass and measure 175 mm and take B as a center point and cut the arc, right. So, still we have to find the point C. One more data is also available, CD which is equal to 112.5 mm, right. So, already we know that the point D. So, take a compass and measure 112.5 mm, 112.5 mm and take D as a center point and cut the arc. Then finally, we got the point C. Join all the points, right. This is configuration diagram. This is how we have to draw the configuration diagram. So, first step is over. Then the second one is calculate the velocity of the input link, right. So, input link which is equal to the link AB, right. Here the data is given. What is the formula for calculate the velocity of the input link? So, velocity of B with respect to A which is equal to the angular velocity of the corresponding link into the length of the corresponding link, right. Here the crank AB rotates at 10 radian per second clockwise, right. So, that is why in the configuration diagram direction which indicates clockwise direction and the angular velocity which is 10 radian per second for the input link AB. So, we have to substitute omega BA which is equal to 10 and length of the link AB which is equal to how much? 62.5. We have to convert into meter, then substitute 0.0625, then multiply this, then we got velocity of B with respect to A which is equal to 0.625 meter per second, right. Once we calculated this input velocity, then draw the velocity diagram, right. How to draw the velocity diagram? Already we discussed in our previous video. Take a look once, okay. So, directly we will go to fourth step. So, measurement of VCB and VC from the velocity diagram, right. So, this is VB and this is VCB, right. Measure this vector BC, right. So, measure this vector BC and multiply with the scale, then we got 0.35 meter per second, right. So, what is the formula for velocity CB? Velocity CB which is equal to angular velocity of CB into the length of the link CB, right. So, from this, so this is velocity of CB we got from the velocity diagram, right, and we have to find the angular velocity of omega CB. So, omega CB which is equal to the velocity of CB divided by the length of the link CB, right. Substitute the values, then we got omega CB which is equal to 2 radian per second. Similarly, we got this velocity of c from the velocity diagram, which is equal to 0.44 meter per second, and velocity of CD, which is equal to omega CD into the length of the link CD. So, we have to find this omega CD, so which is equal to velocity of CD divided by CD, right. So, which is equal to 3.91 radian per second, right. So, these first two things we got, we calculated omega BC calculated, omega CD calculated, which means the angular velocity of BC and CD calculated. Now, we are going to find the angular acceleration, which means alpha BC and alpha CD we have to find, right. So, constructions of acceleration diagram, right. So, first we have to construct the acceleration diagram. Before start to construct the acceleration diagram, we should remember 2 points. The first one is the radial component, acceleration of radial component is parallel to the link, but the direction is towards center of rotation, okay, center of rotation. The second point, acceleration of tangential component is perpendicular to the link, corresponding link, right. So, we should remember these 2 points before start to draw the acceleration diagram, right. So, values are here already. So, first we have to discuss how to draw the acceleration diagram. So, this is velocity diagram, already we know that. Now, this is okay. Now, we are going to draw the acceleration diagram. So, from the configuration diagram, so what are the fixed points? Point A and point D. These 2 points are the fixed points, right. So, first we have to fix the point. Before that, here I want to draw the configuration diagram, right. So, this is actually A D, right, and this is 60 degree inclined line, right, 60 degree inclined line. This is B, and this is C point, and we have to join this BC, right. This is the direction, input link direction AB. Oh, this is the configuration diagram, okay. So, now fix the point A D, A dash comma D dash, similar to here A dash comma D dash. This is the fixed point, right. This is the fixed point A dash comma D dash, because in configuration diagram point A and point D both are fixed points. Now, take the link AB, input link. So, input link, what is input link? What is the acceleration of radial component? What is the formula? Acceleration of radial component of link BA, which is equal to, what is the formula? Omega squared of BA into the length of the corresponding link, right. So, we have to alter this formula, velocity of BA, which is equal to omega BA into the length of the link AB. This is the formula for velocity of B with respect to A, right. So, now square both sides, right. So, velocity of BA squared, which is equal to omega squared BA into length of the link squared. Now, omega squared BA, which is equal to BA squared divided by AB squared. Now, substitute this value here, then the equation became acceleration of radial component of BA, which is equal to velocity of BA squared divided by AB squared into, here one more AB is also there, AB. So, AB cancel. What is the final formula? Velocity of BA squared divided by the length of the link AB, which is equal to acceleration of radial component of BA. So, this is the final formula to find the acceleration of the corresponding link, whereas if the link which is equal to changes the acceleration of radial component of BC, which is equal to velocity of BC squared divided by the length of the link BC, right. This is the formula, right. Understood? Now first we have to calculate the input link BA, velocity of BA, acceleration of radial component of BA, which is equal to velocity of BA square divided by AB, right? So now acceleration of radial component of BA, which is equal to velocity of BA squared divided by BA, right? So now this is we got from velocity diagram, already we calculated, or we can get from velocity diagram, and this is the length of the link, already we calculated. See, the radial component of BA, which is equal to velocity of BA square divided by length of the link, velocity of BA already we calculated, square divided by the length of the link, then this is the magnitude of acceleration of radial component of BA. Then acceleration of tangential component of BA, we have to calculate two things for each links, right? So this is input link, right? Input link has two components, one is radial, another one is tangential. Already radial calculated 6.25 meter per second square, whereas for tangential alpha is not given in the problem. See, in the problem alpha is not given, right? So only the angular velocity of the input link is given, angular acceleration is not given, then we taken or we consider this alpha which is equal to 0, right? So totally, so for this alpha which is equal to 0, so multiply this alpha with the length of the link AB, then the total term became 0. Then acceleration of tangential component of BA, which is equal to 0 in this case, right? Now magnitude we know that 6.25, right? So what is the direction? Direction which is towards the center of the rotation. Here the center of the rotation, I mean the link AB, the link AB from A to B, from the cursor moves from top, bottom to top. So the centripetal component, it moves from bottom to top, right? Because the direction towards the center of the rotation, right? So B point with respect to A, right? So we have to draw the parallel line but in opposite direction for the corresponding link AB, right? So here the link AB is there, so we have to draw a line parallel to this link AB but in the opposite direction. See, point A to B, here the point A, we have to draw the line towards bottom and it should be parallel to the link AB. And what is the magnitude? 6.25, right? So draw a line parallel to the link AB but in the opposite direction. This is actually B dash, right? A dash is there, then B dash is there. The magnitude which is equal to 6.25, or take suitable scale according to that, right? So now consider the link 2, which is B and C. So we have to calculate the acceleration of radial component of BC, which is equal to velocity of BC square divided by BC, right? So for link BC, the acceleration of radial component of BC, which is equal to the velocity of BC square divided by the length of the link. So the acceleration of radial component of BC is 0.7 meter per second. So tangential component we can't calculate because we don't know the value of alpha BC, right? So now 0.7. So we have to draw a line which is parallel to the link BC but in the opposite direction. See, the cursor moves from B to C, from left to right. So we have to draw the line parallel to this link but in the opposite direction, right? So see here, point for the magnitude for the acceleration of radial component of BC, which is 0.7, right? So 0.7. So this is the end point. So I want to give the name X dash, right? This is the radial component, acceleration of radial component of BC, right? So now we have to draw the tangential component. First we have to draw the radial component, then tangential component. Tangential, we know that the tangential component is always perpendicular to the corresponding link BC, right? But the magnitude we don't know. So for that we have to draw a line on both sides, bottom and top, right? Magnitude we don't know, right? Now take third link CD. We know that the point D, right? So now we have to calculate the acceleration of radial component of the link CD, magnitude. We have to calculate the magnitude of acceleration of radial component of CD. So acceleration of radial component of CD, which is equal to, what is the formula? Velocity of CD squared divided by the length of the link CD, right? So already we calculated. See, the acceleration of radial component of CD, which is equal to the velocity of CD divided by the length of the link, which is 1.72 meter per second squared, and tangential component we can calculate, right? So now that radial component of this CD, which is parallel but in opposite direction, right? So the cursor moves from D to C in bottom to top. Here we have to draw from top to bottom. That line, it should be parallel to the link CD, right? With the magnitude which is equal to 1.72, right? So 1.72. So the end point which is equal to y dash, right? So now we have to draw the tangential component, right? Tangential component, for tangential component we don't know the magnitude, but we know the tangential component is perpendicular to the corresponding link CD. So through this y dash we have to draw a line. That line, it should be perpendicular to the link or perpendicular to the radial component, right? So here we got the cutting point, right? So this is actually C dash, right? So join this C dash with A dash and join this C dash with P dash, right? So this is actually acceleration of CB, right? So this is acceleration of CD, which is equal to acceleration of C, right? Because D is a fixed point, that's why we have to assume this is acceleration of C, right? So this is actually acceleration of radial component of CD, and this is acceleration of tangential component of CD, right? And this is acceleration of radial component of BC, and this is acceleration of tangential component of BC, right? Now the magnitude for this A dash B dash, which is equal to 6.25, right? So this is, we have to measure from the diagram, acceleration diagram, C dash B dash, right? C dash B dash, which is equal to so and so value multiplied with scale, if you fix that scale, right? That is actually meter per second squared, right? Now see, this is the value we measured from the acceleration diagram. So this is the radial component and this is the tangential component. So the vector y dash and c dash, which is equal to the acceleration of tangential component of CD, right, which is equal to 5.5 meter per second, whereas here the vector x dash and c dash, which is equal to acceleration of tangential component of CB, right, which is equal to 4.2 meter per second. So we know that, so acceleration of tangential component of CB, which is equal to alpha CB into the length of the link CB, right. So we want to calculate alpha B CB, which is equal to acceleration of tangential component of CB divided by CB, so which is 24 radian per second squared is the value for angular acceleration of the link BC. And similarly we have to calculate the angular acceleration of CD, which is equal to acceleration of tangential component of CD divided by CD, which is equal to length of the link. So finally we got 48.89 radian per second squared. This is the value for the acceleration of the link CD. Okay, thank you.